All right, so there's all sorts of let's see. So there's all sorts of other interesting things in the slides for chapter 1 that I just want to not briefly go over, but mention that we're going to go over them later in class, or mention they exist, right? So the slides happen to cover some stuff that I'll go over later, like they go over abstract classes, which we're not really going to use too much here. But they're going to go over, they go over the object class and its dot equals class. Errors, which you're going to have to do, which will be your first assignment, is just going to be something along the lines of handling errors, probably. See. And then what was the other thing? They have, I think the only thing that they really go over is the instance of class, which basically says, hey, is this object an instance of some other, is it this type of object? And then wrapper classes. I think they mentioned it somewhere in here, but we're gonna get to that when we go over that in chapter 2. When we get to that in chapter 2, as I mentioned, chapter 2 is going to be, it's going to be quite a bit of material. In fact, we're going to spend most of our class in chapter 2. So most of this first part of class in chapter 2, a couple of weeks. I mean, normally it takes me to week 4, but since I've went ahead and removed the whole let's get started with the syllabus thing and push that off to video, we should actually be able to make good time to it. I generally do my first exam at around chapter 2, so you should expect your first exam either during the 5th week or the 6th week of class. And I'll give you more information as you get to it, but that will be taking place during the lab. You'll also have a timed lab at some probably around, not this week, not next week, but the week after that. And that's kind of like a mini exam. It will be around 5% of your grade. So that sounds like a lot, but the idea here is that this first lab will be, a bunch of review. Like, let's review the whole, let's make a complicated class by making a kind of game. Second one is going to be a bunch of exercises that you have to write programs for. So it's a basic list manipulation kind of deals. And then this third lab will be more the same, and I'll also be giving you a worksheet to take home as homework as well. So third lab will be, rather than, well, you'll get basically some math homework to do. Which is weird, but computer science and math is, we used to be a part of them until we seceded, so. All right, with that, let's go ahead and open up the PowerPoint for chapter 2. So lists and the collection framework. Now, the reason this is going to take so long to do this is because display sweat. Let's duplicate the slideshow. Okay. Is there a way to do that by default, or is it just going to keep doing that all the time? All right, slideshow, set monitor, use presenter view. There we go. 5. Wonderful. Okay. So the reason this is going to take so long is because we're going to learn how linked lists work, and we're going to really get into the weeds on linked lists. But once we are done with this chapter, right, this one's going to take a while. So like, how are we going to be able to cover the entire book if this one's going to take a bunch of weeks? Well, it turns out after we do this, since stacks and queues, which are chapters 3 and 4 respectively, are really just dumb linked lists. They're linked lists that are just scaled down and made simpler. And we've already would have learned linked lists. Then those will take a lecture apiece to do. So one lecture for chapter 3 and one lecture for chapter 4. So let's go get into this. So we're going to go ahead and discuss what a list is, because you kind of have a really intuitive idea, but we really need to pin it down if we're going to be working with lists and creating them. We're going to write 2 different types of lists, an array-based implementation of list. So essentially what we're going to do is we're going to start by writing a smart array, something that will basically be an array that grows and shrinks as we need it. Then we're going to learn how to build different linked list data structures. Singly linked list, doubly linked list, circular. But along the way, in order to, well, I mean, if we have 2 ways, why are we learning 2 ways to write lists? Because one has advantages and disadvantages, and they're, what one is good at, the other one is bad at, and one is bad at, the other one is good at. So, and how do we say good and bad and efficient? Well, we're going to learn about that in this chapter. So there's a whole lot that goes into this chapter. So So let's go ahead and start and define a list, and let's also go ahead and define what the heck a data structure is. So a data structure is a collection of data that we can modify. So, and we modify it in a specific manner. So we're going to be going over a lot of data structures in this class. All right, and let me just go ahead and write them out on the board for us. Let's see. There we go. So we're going to be going over, we can qualify array as a data structure if we really need to. Because, it is a collection of data. It's just a big block, a nice big chunk of memory that's all next to each other that we can add, that we can modify. So, but we're also going to go over lists. And we're going to go over two, as I mentioned, we're going to go over two flavor of lists. Array lists, okay, and linked lists, okay? Array lists and linked lists. And I've already got a lecture up online about array lists, but that was part of me just practicing on how to get this, entire streaming thing working. So array lists, we're going to do two types of lists, array lists and linked lists. And we're actually going to learn multiple types of linked lists, multiple implementations of them. Let's see, what else are we? So then we're going to go and do stacks. We're going to do queues. So you just pronounce that by just saying the first letter and forgetting about all the rest. So then we're going to go over trees, specifically binary search trees. We're also going to go over heaps. And then when we really get into late into the semester, I'll just simply say instead of, we're going to learn about hash tables, which happens to be my particular favorite. And we're going to use those to learn, so we're going to use a hash table to build a set. And we're going to use those to build maps. So sets, maps, okay. And then graphs. And if we have time, maybe I'm going to try to throw more stuff, more advanced data structures in here towards the end. That might not be on the final. Sorry, that won't be on the final because the final is a common final, which means that basically everything in here is everything every other class is going to learn too. Okay, but if we get the chance, I'm going to throw extra stuff in there, and I will be throwing extra stuff in randomly just because it's really cool stuff. So these are the data structures we're going to learn how to implement. These are all different ways of organizing our data, whatever that data happens to be, and then learning how to manipulate them. And they all have their own advantages and disadvantages and also their own purposes. Okay? In order to analyze also just the advantages and disadvantages, we're going to learn about algorithmic efficiency, and we're going to learn about how to describe it in big O notation. Anybody already know that? Big O notation? Yeah, so then you're already ahead of the game there. We're not going to go into it like in the super theoretical mathematic way. That's, I believe, reserved for other classes. Instead, we're going to go for just a layman's understanding of big O notation. Basically being able to understand and kind of feel more than explain what different big O notations mean. Okay. Then we also will go over, along the way, we're also going to, in order to do with trees, we'll also have to learn in detail recursion. And this is where the class really becomes fun. Right after we do stacks and queues, we'll jump over and do recursion, because recursion allows us to do a lot of stuff. Like I'll write a Sudoku solver in class, and we're just going to basically be able to solve any Sudoku puzzle we want, which is a common newspaper puzzle these days. And my way is really stupid that we solve it, but it's a really efficient, stupid way to solve it. We'll also learn about common chess puzzles and other puzzles that can be solved with recursion. By learning recursion, you're going to be able to solve some problems you would have thought were impossible. Okay. Also, we're going to learn a lot about the really common problem of sorting, which gets its own chapter in the textbook. Sorting is one of the most common problems in data, in computer science, because if I have a bunch of data, right, a lot of times I need to put it in order to do anything useful with it. So Sorting is, how do I take this data and put it in order? And there's actually a lot of ways to do that. And of course, they'll have their own advantages and disadvantages that we're going to have to learn, right? We're going to learn a whole lot of sorting algorithms. Like, I'll probably go over 7 of them, but for the exam, you're going to need to know 3 of them. So I'll go over a lot of them, but at the end of the day, for knowing what you need on the exam, you're pretty much going to know the most important 3. So again, a lot of stuff gets covered, but we're going to spend but chapter 2 covers this list stuff as well as the big O stuff. So a lot of stuff gets covered there. So that being said, let's go ahead and talk about lists. So we kind of have an intuitive understanding of what a list is, right? You probably have made a to-do list at some point in your life, right? You probably said, and here's a common one, a shopping list, right? Okay. So let's go ahead and use the shopping list metaphor to actually talk about what we expect from a list, right? So a list, it defines as a collection of elements, each with a position or an index, right? And that makes sense. When I'm making the shopping list, like you probably did when you saw that major snowstorm come in a couple weeks ago, you probably put 2 things on your shopping list at the top. What were they? What does everybody put on the top of the shopping list? Bread and milk. Bread and milk. You got to get the bread and milk because always go for the stuff that's going to, perish if this power goes off. The bread won't. It'll last, but it's perishable. But the milk, definitely want to grab that just in case the power goes off. Don't know why. Probably eggs because I hear French toast on snow days are fantastic. Right. So and if we go through this list, we'll say the first thing in this list is bread. The second thing in this list is milk. The third thing in this list is eggs, right? First, second, third, although since we're computer scientists and information people, we're going to, say this is index 0, index 1, index 2, because everything's going to start from 0 just for consistency's sake, okay? Right, index 0, index 1, index 2, first thing, second thing, third thing, okay? So, actually, I'm just recording that, so that was probably really tiny. See, I told you I'm getting the hang of this right now, so... All right, so we've got bread, milk, eggs. So with a list, what we want to do is basically be able to really add stuff very quickly to this list. So bread, milk, eggs. What else might we want on a shopping list if we're snowed in? Any suggestions? Turkey, ice cream. Okay, so turkey. Why not? Ice cream. I like ice cream, even though it's going to be a cold day. I might do some hot chocolate. In fact, I like it so much I'm going to put it at the top of the list, right? So nice thing about lists is that we can put them at the top of the list, right? Hot chocolate. Right? Okay. Maybe I take a look though and I see that I already have bread at home and I don't need to pick up another loaf of bread. So another thing we want to do with lists, right? We want to just be able to remove things from the list, right? Now, what also happens when we do this is that bread was the second thing in the list, but now what's the second thing in the list? Milk, right? So a list works exactly like you think it would, right? We can add stuff wherever we want in the list, right? But it's always consistent, right? There's no gaps in the list. Even though there does look like a gap here, we aren't saying that this is the third thing in the list, even though we've got a gap here. It's the first thing, second thing, third thing, fourth thing, fifth thing, right? It's got 5 things in the list, not 6, even though there's a physical gap here, but logically, there's 5 things in the list. They're all next to each other, right? We can add anything we want, anywhere we want to in the list. And we can remove anything we want in the list. I can also maybe say, okay, I can also say, what is the third item in my list? What is at index 2? Eggs, right? So I can also just look at something in the list. Or I can also maybe swap that out. Maybe I'm not a turkey guy. Maybe I'm a chicken guy, right? No, nothing against the guy who chose turkey, but so it's just an example. So we can add things as we want to this list. We can remove things from this list as we want. and we can we can get and set things. So it does resemble in a sort of a way what we would want with an array, right? You can create an array and it's full of a bunch of empty slots, and you can put something into an array, and you can get values from an array. But the issue with an array, right, is that you can't just arbitrarily add something to the front of an array, right? Because it's already items there. You'd have to move them out of the way. And you can't just remove something because that would leave a gap. But we'll get into that. So, so we have this hierarchy of lists. There's a lot of different ways we'll learn how to implement a list. The two we're going to go over is array list and linked lists. And there's this nice chart over here which goes over them. So java.util interface and its implementers. So what is an interface? That was something that was, again, that I said I'm going to just skip over until we have to deal with it. What is an interface? So again, we're going to use that blueprint metaphor, where we had the idea. We already used it once, but we're going to use it again, even though that might get confusing, right? We said basically a class is a blueprint for an object, for building an object. Well, a interface is a blueprint for writing a class. Basically, we're going to say is that we have this list interface. Java has this list interface, and we say, and Java's saying to us, if you want to write a class and you want to consider it a list, then I'm going to have a bunch of methods that you need to fill out and create for you to be considered a list. Okay, and there's a lot of different interfaces in Java. They're essentially blueprints for writing a list. So a list basically says, here are a list of all the methods we need. Abstract list is an abstract class that's kind of halfway between a class and an interface. It says, here's some of the stuff already filled out, but not all of it. Okay. So we use it. So an interface acts as a guide for building these things. So let's go ahead and actually take a look at the actual Java list. And we can do that because, you know, actually the source code for everything in Java is just something you can look at. So let's go ahead and say, just to start off, we're going to look at the string interface. So not the string interface, but string class Java. We're going just to show you that you can do this. So string source code. Okay, and I'll probably have to zoom in for this. So let's go ahead and look at the raw. Okay, and come on. So string class raw. I was aiming for zooming in. That better for everybody to see, even though it's just a bunch of text? Right, so here, just to prove it to you, over here says public final class string implements all these things. All right, so let's go ahead and just showing you first, saying that it's in the package java.lang, and here's all the stuff it imports. It imports strings happen to use array lists to work. They use that somewhere in there, and it uses a bunch of other stuff. All right, so the first thing it does is says it's public final class string. What the heck is a final class? We've seen final before, right? Like we've seen it over here. Final character value. Final int offset. So so let's go to the familiar. What does it mean when we have a final variable? When we create a variable and make it final? It can't be changed, right? Okay, so final means can't be changed. Like a common example of this is when I write maybe a circle class and I say public static final pi is equal to 3.1415, right? And this is where I make a variable public, which would normally mean anybody could change it, but I don't want people to change pi. That would mess things up, right? But I do want people to easily be able to get access to pi without them changing it. So I can just make it final and say this is the value for pi, don't change it. Okay, so final means don't change. So, and it means you can't change this in all the contexts. So if that's the case, what does a final class mean? I'll give you a hint. It has something to do with inheritance. Any guesses? So final means it can't be changed, and it has something to do with inheritance when we apply it to a class. So what does that mean? Yes?
For that class, you can't create something under.
Yeah, you can't create a subclass. That's exactly correct. You cannot create a subclass if you make it final. So final classes means you can't. Basically, it's a way of you getting a lot of control over your code, saying that you can't make a subclass of this because you might change it. Right? We don't want somebody to change string. They don't want to make a subclass of string and then use it instead of a string. That would kind of maybe mess up how strings work. You might change some really crucial behaviors. No, string is done. We don't need any improvements on string. Okay, that's kind of the idea. You can also apply final to a method, and it does very much the similar thing. It means that the class below you can't override it, right? You can't if you use final on a method, then let's see if they have anyone over here. Probably does, but we're still in the constructors because, of course, we are. So, yeah, I'm not going to bother trying to look for one if I can't find it immediately. So final methods, basically, so you would like the public final int foo and then parameters. It would basically mean those are just methods you just can't change. You can't change them when you override them. Okay, so you can go in and you can look at all the code. And you notice that it implements, right, where I said you can extend a bunch of interfaces, right? Sorry, so you could extend, you can extend one single class, but you can implement a whole lot of interfaces. So let's go ahead and just, because this is something you should have learned but may not have had time for, so let's go ahead and just make sure. Let's go ahead and write a class in inheritance. Actually, we're not going to write a class. We are going to write an interface. Very common interface that we like to give an example is a shape, right? Shapes are so weird that I can't really say, like, this is one shape, or, I can't really define a behavior for them. But I can define some common things about shapes. What are common things about, what things are common in shapes? They have areas, that you have some way to calculate an area, and you have some way to calculate a perimeter, right? So, public, so let's say, public double get area. So notice that to create an interface, all I do instead of writing class is that I write interface instead. It's still a .java file. I just use interface instead of class. And this is how you do, is that you just simply define what methods, if it's a shape, that the class is going to have. If it's a shape, then it's going to have a method that gets the area. Notice that there's no code in there. In fact, it's illegal for me to try to create any code. It gives me an error saying that abstract methods do not specify a body. Abstract methods, well, anything that's in any method that's inside of an interface automatically has an implicit abstract keyword added to it. And notice it doesn't throw any errors there. This just like how any object automatically, anything you write, if you don't extend anything, it automatically extends object. Similarly, going on over here, you automatically get an abstract thrown on there. And an abstract method is just simply one where you say my subclass, anybody who inherits me, is going to define it. Okay, that makes sense? Anybody who implements a shape has to define this in order to be considered a shape. That makes sense? How they do it, that's up to them. They could just return 0 if they wanted to, right? But if you implement a shape interface, you gotta be able to define a area, and you've got to be able to define a perimeter. Make sense? Okay. We can't actually add too much. Like you can't, and that's about it. You can't like do anything else like this in X. The only variables you can add are finals. You can only add like constants to an interface. So they make them really easy to write. An example of how you might use this is maybe we'll create a circle class. Okay. And circles, all you care about, and I like circles because unlike other shapes, they're really easy to do because all you have is a radius as the only parameter that you need for it. So private double radius. This dot radius is equal to the radius that's been passed into me, right? So really we only need one parameter that defines the circle. A radius is all that defines the circle, right? Maybe if it's graphical and on a plane, you might need an xy, in which case we can extend the class, right, and add in an x and y coordinate. But other than that, circles, they just need a radius. And useful enough, we might do a public static. And I'll go over why this is. I'll go ahead and go over why this is static as well. Public static double pi. A lot of keywords thrown around on that poor pi, you know. Okay. Final meaning that public meaning that anybody can read it. Final meaning that nobody can write it. Static means that basically it exists. Since it's a static variable, that means that we have one pi variable that's shared among every single circle. That means if we create 1,000,000 circles, we don't have 1,000,000 wasted double. We don't have 999,999 wasted doubles, right? Instead, we just have one variable that's shared among all the circles. Okay. Now, but again, I want a circle to be considered a shape. Because for polymorphism purposes. So what I do in order to make it to say it's considered shape, I say implements. Implements shape. So now that's going to give me a couple of errors saying, hey, this is a circle. It says it's a shape. You have two things you need to do. The first thing we can do is that we can make it an abstract class, which means that it's got some stuff that's defined in it, but an abstract class, you can't create an abstract class because it's not finished yet, right? You can't make an interface. You can't just create, I can't just go and create a main method and say, hey, create a new shape because the shape has a bunch of undefined actions in it, right? That makes sense. You can't create it if it doesn't exist. An abstract class is similar. It's just a more complete version of a class. So there's a more complete version of interface. It's kind of the halfway point between a class and an interface. And all an abstract class is and means is that it means that basically it's a class that has abstract methods in it. Okay? You don't find them too much, you won't be really writing any of them for this class, but they're just a thing to know that exists. The way we handle implementing interfaces is that we will actually implement the methods there. So we have to create. So we create a getArea method, and now the compiler is happy because I'm calculating the error at the area and it's returning 0 for it and the perimeter. But so yeah, those are totally wrong, but at least I have something down, right? You know. So let's go ahead and actually calculate the area, which should be pi r squared, right? So pi times radius times radius. Okay, and then pi. So and then 2 pi r for perimeter. 2 times pi times radius. Unless I've completely forgotten my basic math. So let's go ahead and just make a public static void main string args. And so we can say shape S is equal to and so we can just do this like we would normally do any kind of polymorphism. So we create a shape variable that we can fit any sort of thing that is a shape into there. Now, we can't create a new shape because a shape is an interface, right? A shape doesn't really have anything. It's just a bunch of, it's just a very tiny to-do list. List, as we'll see, is a giant to-do list. So let's go ahead and see that just for example. So my list, okay, interface is add the list interface from java.util. Add it, okay. So finish. So it says, hey, you got to implement all these lists. Oh, and it's got this weird E thing on that. That's a generic. We'll worry about that later. We'll burn that bridge when we get to it. But it says, okay, actually, in order to be considered a list, you have to implement all these methods. Don't worry, we're going to be working on a reduced subset of these, so we're not going to actually go over all these 23 methods. Just the ones that basically require some mental thought, and the rest are actually fairly straightforward to do. But as you can see, this is list is a very big to-do list of methods to implement, right? Shape, not so much. But you can't create a new shape because it's just a to-do list. It's just a bunch of stuff to do, right? But we can create a new circle of radius, let's say 5, right? Because a circle is a shape, and it is a defined shape, right? So we define interfaces. You're not going to be having to write a lot of interfaces here. That's why I'm kind of just glossing over it. But the idea here is that I just want you to know enough about it so that when we look at it, you're not completely confused. Okay, so shape S is equal to a new circle, and then S dot get area. System.out.println. So I was hoping this was stuff covered in 1068, and it probably was, but oh, where am I getting my error? Oh, yeah, because I defined a bunch of methods in my list that I don't need anymore. Okay, so run this, and this is something that resembles the actual radius because pi's not as much of pi as it could be. Actual area, sorry. All right, so moving on. So list, right? So list source code, right? So I do go off on tangents like that just because sometimes we need to explain stuff in this chapter. But I prefer explaining it with stuff we're actually going to use rather than weird abstract examples. So here's the list interface, right? It's in the java.util package. And it looks kind of scary, right? Public interface list E extends collection. Wait, you can do that? You can. Well, it turns out that lists can extend other interfaces. So a list can be a list is a type of collection. So interfaces can extend a single other interface, which just simply means it just adds on to the previous interface's to-do list. So it says, in addition to all the other stuff in your collection, you also need, so not only do you have to implement my stuff, you also have to implement collection stuff. What the heck is this weird E thing? Well, the weird E thing is called a generic, and we'll get to it. It looks scary. It's really not. It's just a placeholder variable, which says basically when you define this, you can put anything you want in here. So you can make it a list of integers or a list of strings and basically make it a list of a single thing. And there's a lot of reasons. And I go to this in the side video, but I will address this in class because it's super important that we understand this. But let's go ahead and look at like all the things that you need to do in order to be able to consider a list in Java. What are the things that a list does? Lists have a size. We can tell a list whether or not a list is empty. That makes sense, right? Okay, and you can even kind of figure out how to do that if you have a size working, right? If the size is 0, we're going to return true. So, right? Empty lists don't have anything in them. Does it contain an object? Iterator or iterate, okay. 2 words, that's confusing when you've got the same word over here. But what this does is that this returns an iterator, which we'll get into, but that's just a way to go through the list sequentially. Okay, turn the list into an array. That you can see why that might be useful. Sometimes it's just useful to turn stuff into arrays. Okay, but it's not really what makes a list a list. And then you have this gobbledygook over here, right? T's and t's and to array, and okay, we'll just ignore that for now because it looks scary, right? Okay, Boolean add EE. So that, I guess we're just adding something to the list. Boolean remove, okay, we got to remove something from the list. I'm going to stop looking at these arguments and just look at the methods. Figuring out if it contains all the things, if this list has all these things. Add all the things to the list. Oh, that looks scary too. I don't want to think about it, right? So don't worry about it. It's actually a lot easier, and we'll build up to it. We're going to start with simple examples and build up to it. Add all the things. So again, just focus on these. Remove all the things. Retain all the things. Okay, that's weird. Equals get, set, remove, index of operation. So just a bunch of just to-do lists. But a lot of these make sense, like getting and setting stuff in the list. Like that means, okay, getting a value from the list, changing a value, or looking at what it is, and then adding and removing things from the list. That makes sense. Okay, so I think we know enough now to continue on with this. So a list, an abstract list means it's an abstract class, which means that it's some of the stuff already figured out, but not all of it. An array list means that we use an array to build a list. And that's where we're going to start. And then the linked list will, that we use, I guess if we use an array, we use links to build a linked list. So, so an array and lists are actually really similar, actually, as I was kind of implying earlier. In fact, in the Python programming language, there is no array. In Python, let's see, this again, let me go ahead and up the console size. So I'm kind of biased, by the way. I happen to like Python a whole lot. So, but in Python, there is no array. There are only lists. So for example, if I want to create a list in Python, all I have to do is say create a, so here 1, 5, 6, 7, 2, right? This is a new list. And here's all the values in the list, right? And then, but even though it looks like an array, it's not an array, because in Python there are no arrays, there are just lists. I can add something to it, so add 4 to the list. Sorry, in Python speak though, they use a different word, append. Always forget that. So 1, 5, 6, 7, 2, 4. Let's see, append. Let's see, it takes exactly one argument. I think it's insert for the other one. I always forget what I have to do. So I've appended 4 again, and now we've got 1, 5, 6, 7, 2, 4, 4. So we can just add stuff to a list in Python. Yes?
Is there an advantage to having arrays if you could just like use lists instead?
So arrays are going to be way more, arrays are way more efficient, like in terms of space. Right, because as we'll see, you can accidentally waste space with array lists. But that's an excellent question. Like, why would we use arrays if we can just use arrays lists instead? Or sometimes it's easier to manipulate arrays and much more concise. You have to be a bit more verbose with array lists, and that's just from a programming perspective. From an implementation perspective, arrays, if you can do it with an array instead of an array list, you should, because it's a bit more efficient. Okay, so, but an array is an index data structure. That means that we've got basically, you know, an index 0, an index 1, and so on and so forth until we get to the end of it. And so with an index structure, that we can go ahead and get values in any order. So we can just, so like our list example that we wrote on the board, we could get the 3rd item in the list, the 5th item in the list. So index 2 and index 4 in those cases, index 0, or we can just go through all of them and iterate through all of them, right? So we can do that with an array, and we can do that with a list as well. But again, here's the disadvantages of using an array. With arrays, as you've probably learned, you cannot increase the length of an array. Once you create the length of an array, it is fixed because you've created this block of memory. So you've created this just static block in memory, and then you can't add it because there might be things before it or after it. If we do have extra space that's unused and we want to put something in the middle, we have to move all the stuff over, and that's an annoying operation to have to do. And same with removing an element. Although we're going to have to do that with an array list. But an array list will at least abstract it. So the advantage of a list is that basically we can, an array list specifically, is that it acts like a smart array. We can grow it and shrink it dynamically. So again, here's all the things that I was saying that we could do with an array. I've already went over them. You can get something at specific positions, place them at specific position, find something, find if that value if it exists, add to either end, remove to either end, or actually any position, and just simply go through it. So all the classes, so the array list and the linked list, all do these things. They just do it in a different manner. Okay. So we'll get into this. The array data structure, classes that implement list interface do not store primitive types. So I'm going to disagree here with not like the concept, but bringing that up first. So let's go ahead and just make an array list to see it in action. So let's go ahead and create a new package for organizational purposes. I'll do that by creating a new class. This will go into lists. Okay. And array list example. So we'll go ahead and create an array list example. Okay. And again, just paranoia making sure. All right. So let's go ahead and create an array list and see how it works in Java. So the first thing is that it's an array list. So let's call this array list is equal to a new array list. Okay, and you're noticing that warnings are going to crop up when I do this. So first we get an error because we have to import it. Import array list. Okay, and you're going to see a couple, so it says we don't use this. So let me go ahead and start using it. List.add 1. So I'm adding the number 1 to the list. Okay, so now we're seeing that we're getting warnings basically on every line I'm writing. And it's coming up with like, array list is a raw type, so it's uncooked. References are to generic type array list that scary E should be parameterized. Okay, we'll get to that, in fact. But we can ignore, because it's a warning, of course, we can ignore it for now. We're not going to ignore it for too long, though. Okay, so we can add 1 to the list. List.add 2. Okay, and then we can actually, it's nice though that it has a nice toString method, right? Every object has a toString method, and because object defines a toString method. If you don't define a toString, by default it prints out a hash value of it, and by default that hash value is the memory is some kind of memory location of it. So, and I'll get into that later on in the semester, but as a result, if you don't implement like a toString method, it prints out a memory location. But list does have a toString method implemented in it. So run it and it says 1, 2. That's pretty useful. So it looks like it looks like an array, right? It's called an array. Seems like it's a smart array that grows. Okay, list.remove. So remove the thing at index 0. Okay. Nope. Didn't work the way I thought it would. What if I say remove 1? Oh, well, what's my problem here? I'm not printing out anything, right? This is a PEBCAC error. Problem exists between keyboard and chair. So remove 0, that removed index 0, right? Okay, so that's pretty cool. What if I try to remove something that's out of bounds, like remove index 4? Well, we get an index out of bounds exception, as you might not be surprised to learn. Okay, so obviously you can only remove things that exist in the list. So we can remove index 1. So we can add and remove things from the list, right? And if you just do like list dot, you'll see a lot of things. You'll also a lot of the time see me, instead of writing array list, new array list, is that I'll use polymorphism and say list is equal to a new array list. Why? Because it's less for me to type. That's why. It's just saying that basically I'm creating a list variable and I'm storing an array list in it, right? We've learned that we can do that because an array list is a type of list. So even though list is an interface, I can store all this is saying we're creating a variable. It's named list. It's of type capital L list. And it's going to hold an array list in it. Okay? So that's that. What else can we do with this? Let's see. We can get a specific object, object at an index. So get what's at index 1. Oh, can't do that though because we removed, right? We had 1, 2. We removed index 1. We tried to get index 1. There was no more index 1. So let's go ahead and fix that by adding 3 things to the list now. So in 1 to 100. Okay, so now we have 1 to 100. We removed the 2, right? Because we removed what was at index 1, and we're left with 100. You know, maybe it will be easier if I just simply do, because we're dealing with numbers, let's go ahead and work with strings. It does get confusing because we can add kind of whatever we want over here, right? So that seems like it's a problem that we might want to solve later. So A, B, C. So we removed the B, and so we're left with C. List.set. We can also change things in here. So let's see, set is equal to so take the thing at index 1 and change it to foo. I believe that's the full correct order for the arguments. So we removed B. C became index 1, became the thing at index 1, and then we said let's set the thing at index 1 to foo. Right? So let's go ahead and add a print line between each of these operations. All right, so it seems like a pretty cool it's like a smart array. It resizes itself as need be. And is there a limit to the size? Yeah, but it's pretty high. So let's watch. For int I is equal to 0, I is less than, let's just add a bunch of zeros there, I plus list.add, and what we're going to do is that we're going to add let's go ahead and change these back to integers. 1, 2, 3, 100, add I to the list. So first off, does it crash? No, I can add as much as I want to the list. Can I really? System.out. Print line the list. It does look like I can add as much as I want to this list. Okay. How do I iterate through it? Well, it's a collection, and rather than using .length, we're going to use the .size command. If it seems like I'm going quickly, don't worry. I'm going to go into much more detail about this because we're actually going to build this from scratch. A lot of the data structures, what we're going to do, rather than just learning how to use them, we do build them from scratch. So, and if we didn't, I mean, this course would probably be a quarter of length, but you also wouldn't get the kind of understanding you need to get. So, for int I is equal to 0, I is less than list.size. So here we're going to run into our first headache using a list, which isn't actually a headache if we use generics, but let's go ahead, print line I. So, sorry, print line, sorry, one second, list.getI. Okay, so we're just going to print out all the things individually, right? Nothing too scary about that. We go from index 0 to, and .size is just like .length. It says however many things are in there. We're going to increment that. We're going to go through, and we're going to get the ith thing and print it out, right? But let's say I want to go ahead and get the ith thing and maybe, multiply it by 2 instead. And there we start getting into a problem. we get an error. It says the operator times is undefined for argument types object int. Okay, I know that's hard for you to read in the back, but it says that the multiplication operator is not a defined operator between an object and an int. Saying that basically, I'm just putting integers into this, aren't I? Well, you might forget to. Well, you can put anything you want into a list if you don't use generics, which I'll get into very shortly. So, right, it's very easy for me to do that because now it's not just a list of integers, right? Right, I've added a string to this list. Changed it, now it's from a link, it doesn't hold just integers anymore. It has a string in it. So, obviously, there's a problem there. Okay, so it's saying, hey, you've got a list, it can hold any type of object. I know you think you put just integers in there, but it can hold any type of object. So, I'm not going to let you multiply it. Now, there is a way to get around that, and that's to tell Java, no. I'm going to cast it. Everybody remember about casting, where you tell Java, no, I'm a professional. I got this. Turns out, no matter how many years you've been programming in Java, or at all, you don't got this. You're going to make a mistake at some point. But it works for this case, where we're now just printing out everything multiplied by 2. But suppose you're like me, and maybe you forgot. Maybe you accidentally messed up. So now we run this, and it prints out the first bit, and it says 2. Exception in thread main, class cast exception. And it's basically saying, let me go ahead and remove this print line command over here. What's it saying? It's saying you can't take a string and cast it into an integer, right? It got to the foo, and I said, hey, turn it into an integer and multiply it. And it's like, can't do that. Sorry. Right? So, first off, there were 2 things here that are really irritating. Okay? The first problem that we have is that, it was a great thing that this list could hold everything, because advantage, it could hold anything. I could just throw whatever I want into it, right? Disadvantage of that, if it can hold everything, then then I have to do something called casting, if I want to make sure it's something. So I have to remember that basically it's a list of integers, right? And tell Java to trust me. So that's problem 1. Problem 2 is that I'm a human and therefore cannot actually be trusted, because we have flaws, and maybe it was 1 o'clock in the morning, and now you completely forgot about this over here. That's some cases where you accidentally added a string and forgot to remove that. So what we need is something first off to protect against ourselves. And the second thing is that normally when we make lists of something, normally when we make a collection, it's normally a collection of similar things. Like when they have a list of integers or a list of food items up there, right? I didn't just randomly throw numbers in there. It was all things to pick up from the grocery store. It's normally a list of the same things, right? That makes sense to everybody? So, but what's really useful, what would fix this problem is, 1, having a safeguard to prevent me from doing this, and 2, having a way to say, no, this list has all things of the same type in it, right? So that I don't have to worry about this casting and remembering what was originally in the list. Because I don't want to have to, honestly, it's good practice, but you're probably not going to do this, where you go ilist to note that it's a list of integers. So the solution to this is called generics, okay? Where basically we can write objects to hold other objects of a certain type in them. So right now, and it's best to show you through example, and then we'll get into how this works when we pick up next time. But I want to show you how to use it so that you can use it for your first lab. So here we have those scary less than and greater than signs. Okay. So a couple things. So now I'm saying it's a list of integer. Okay. And what this is that basically is that if you have an object that is generic, remember we were getting this warning that says references to the generic type array list should get parameterized. It just simply meant we should add what's called the generic parameter to it, which is simply this bracket thing. We need to put something in here. And this just gives us a way to say, I want this list, and I'll go ahead and just show you first this example before I go into integers. I want this list to hold just strings, right? Does that make sense? So now this list is going to hold just strings, and I'll match it on the other side, right? Makes sense that I got to match it, right? I can't say that this is a string, this is a list that holds strings, and I can't just put this is a list of that holds integer and expect them to mesh together. That's not gonna. That makes sense why that wouldn't work, right? They don't match. So I'm saying this list is a list of strings. And now what's cool about this is that if I go list.add, it's hard to read for you in the back, and I'm going to figure out how to change the text size. But it says list.add. It doesn't say object down here anymore. It says string. Now, if I change this to something like, so what other things could I do? Well, maybe it's a list of, let's see, scanner. You've all used scanner before. Maybe it's some weird list of scanner for some reason. I don't know why you would want that, but hey, I'm just trying to choose something that you have seen and is an object, right? So now this changes to list.add scanner, right? So I can only add scanners to this. So now, again, I can only add strings to this. So if I do list.add, so now I no longer can add just anything I want here, right? It gives me an error. It says you can't add an int to this. All right. So great. Let's go back to our previous example, right? Uncomment this out. And if I have a list of strings now, this gives me all errors now because I'm trying to add ints all over the place to this list of strings. So let's change this to a list of ints. Now we can put int. So, however, this is going to give us an error there. It says the dimensions are missing. So this is a weird error. This is because it's expecting an integer array, and you're like, why? Why in the world? Well, I just said, well, it's because you can put any class type you want in here. Any class type. And remember, ints aren't classes. They're primitives, right? So this leads us into wrapper classes. So how many of you have seen the integer class before? Yep. So the integer class is, I know this is so much new material coming at you all at once, but don't worry. A lot of these things are pretty straightforward. So that fixes that. So what is a wrapper class? Oh, and we get an error here now because we can't change the thing at index 1 to a string anymore. So that's nice. So that prevents us from accidentally adding a string to our list. And now we can do this with this magical integer class. What the heck's an integer class? Okay. So these are a special set of classes called wrapper classes. Now, sometimes we really can't just use a primitive, right? Everything in Java is an object except for the primitives. So int x is equal to 5, right? That's a primitive. That means we, instead of storing a memory location inside of x, we store an actual value in there. Yes, I'm aware of what time it is, and we're almost done. So just hang in there. Promise it will be over soon. Okay? So an integer so wrapper classes are special classes where basically they're made for when you need to treat a primitive like a class. So I can say int x is equal to, so this is pretty easy to demonstrate, system.out.print line I, right? So integer I is equal to x, right? And what a wrapper class does is that an integer wrapper class automatically converts from an int to an integer. And it'll do the same thing as well. So if I need to add an actual int value to it, it'll say, let me look at the value. I'll just automatically unbox it. So converting, boxing, and so converting in primitive to a wrapper class is called boxing, unboxing, or this one, not too important for that. But what's cool is that also you can do it the other way around. Int y is equal to I minus 2. Right? So you can automatically convert from the wrapper class to the primitive and from a primitive to a wrapper class. And as you could expect, that for every primitive, there's a wrapper class. So double D is equal to 3.5, right? So what do you think the wrapper class for it is? Capital D double, right? Right? Not too hard. Instead of Boolean, B is equal to false. We have Boolean, capital B.
What about string?
String isn't primitive, right? Right? It's just a special, it's just used so often we get to treat it like a primitive, right? We don't have to use the new constructor. And same with the wrapper classes. So string, just gotta remember to give it a name. All right, characters is so char C is the only weird one. And it's not too weird, it's just, it doesn't let you do char C. Instead, it's character C. I don't know why. Okay, that wasn't a design choice I got to have input on. So, so for every primitive, you get to, let's see, is it every primitive? Float f is equal to 2.5? Yes. Yeah, for every primitive, you get that. You have a corresponding wrapper class. So that's pretty cool. So as a result, this is a list of integers, and so you can just add ints to it, and it'll automatically be converted to an integer. And when you need to use an integer, it'll automatically be converted back into an int. So this is particularly useful, as you can see. So it's just a weird quirk of Java. But to make a list that just holds integers, you just say list of integers. If I wanted to have a list that just held doubles, I would say a list of doubles. But let's see about this. Double list. Now, does it do this? Now, of course, this is where it gets a bit tricky, right? Normally, we can automatically convert from an int to a double, right? But here, you're trying to add an integer to a list of doubles. And it says, hey, you're trying to add an int. I'm expecting a double. You really need to add a double here, okay? So we'll learn more about how to do generics next time and how to write them. But this is how you use it. And notice all the warnings are gone. And it's just a nice way to protect yourself. So the way you read this is list of integer. That's all this is. We'll learn how to, manipulate these more next time. This is enough for your first assignment. And I'm trying to remember if I include this in the first assignment. Certainly for your second. There are some weird quirks for using generics, but I go over them in good detail, and that's also why I record the lectures, so that you can always refer back to them.